Okay, so the aim of our experiment is to find the half-life of protactinium using the protactinium generator, which is the smallish plastic container you can see on the screen. Unfortunately, due to its age, I have to send it for disposal shortly, so I thought I'd take it out for one last spin and record the results for posterity. Now we're going to be finding the count rate every minute from the protactinium generator and using that to plot a graph of count rate against time and then read the half-life off of the graph that we've drawn. Having a look at my setup, you can see I've got a clamp stand holding a Geiger-Müller tube or Geiger-Müller detector. Then that's plugged into a counter that will register every time the Geiger-Müller tube detects ionizing radiation, in this case beta, and then we've got a stop clock to measure the time elapsed. At the top you can see we're going to find the background count rate before and after the experiment and then find an average. We're also going to need a results table like you can see here, so get copying that out. If you want to save some time you could just write out the bits in bold, although bear in mind it's always good practice to include your units in results tables. As I already alluded to, our first job before we introduce the protactinium generator is to measure the background count rate so that we can account for this when we process our results later. I'm going to start the stop clock and reset the counter simultaneously, and general wisdom here is that due to the random nature of radioactive decay, we need to wait until we have at least 400 counts, which might take a little while. We've now met our criterion of at least 400 counts, so I'm going to take a reading at 22 minutes, which we can then convert into counts per minute by dividing by 22. Okay, so that's 407 counts in 22 minutes, so you can work out the counts per minute and then add that to your results. You can see I've fetched the protactinium generator from the radioactive store. Now, the protactinium generator has two immiscible fluids inside, and when you shake them together and force them to mix, it creates metastable protactinium-234, which emits high-energy beta particles which are able to penetrate the plastic bottle and are detected by our Geiger-Müller tube. Having given the bottle a shake, you have to leave it to settle for about 30 seconds before you begin your measurements, and then we'll measure the total number of counts every minute for about 8 minutes. The reason being that due to its relatively short half-life, after about 8 minutes it's difficult to distinguish the counts that are coming from the source from the background radiation. I've allowed the protactinium generator time to settle, so let's start the stop clock and reset the counter to begin the experiment. We'll read the total number of counts every minute, and by subtracting the new count from the previous count, we'll obtain the average count rate in counts per minute from the previous minute. So get your pen and calculator ready. Okay, after the first minute, the total number of counts is 273. And after 2 minutes, the total number of counts is 437. After 3 minutes, the total number of counts is 555. After 4 minutes, the total number of counts is 628. After 5 minutes, the total number of counts is 681. After 6 minutes, the total number of counts is 714. After 7 minutes, the total number of counts is 738. Okay, so our final reading after 8 minutes is going to be 759, so we can stop taking readings there and then take the Protactinium generator back to the radioactive store. Now the Protactinium generator's gone, we just need to measure the background radiation again, since for various reasons the background levels naturally fluctuate over time. If the results were to deviate significantly from the ones we obtained at the start of the experiment, we might need to repeat the experiment again in order to ensure the validity of our results. Now that we've achieved our criterion of a minimum of 400 counts, let's take a reading once the stop clock hits 22 minutes again, same as last time. I make that 430 counts in 22 minutes, so you can make a note of that and then calculate the average background count. Note that best practice is, rather than combine the rounded results for the counts per minute at the start and the end, combine the total number of counts as shown on the screen and then round the final value to the nearest whole number. Okay, now you might have been doing some of the maths as we went along, but just to illustrate what you would need to do, for the first reading, the raw count rate is just the same as the total count, and then to obtain the corrected count rate, we just need to subtract the average background count rate of 19 to give us 254 for our corrected count rate. For the second minute, we have to subtract the previous total count from the new total count in order to obtain the raw count rates for the previous minute, and then subtract the average background count to obtain the corrected count rate of 145. And then you'll need to continue for the remaining data and then plot a graph of corrected count rate on the y-axis against time elapsed on the x-axis. Hopefully you've ended up with a graph that looks a bit like this. What we need to do is read off the time interval for the corrected count rate to half. I've gone for an initial reading of 220 counts per minute and then read off the time taken for the corrected count rate to drop to 110 counts per minute. Reading from my line of best fit suggests the half-life is about 1 1/3 of a minute, so that would be 80 seconds. In a perfect world, that would be a little bit closer to 70 seconds. And then just a few pointers in case you're ever asked to explain this methodology. Firstly, due to the random nature of radioactive decay, you want to average for a long time, ideally at least 400 counts. Unfortunately, because the protactinium has a very short half-life, we are precluded from doing that during the kind of main part of the experiment, so we're only able to do that during the background count at the start and end of the experiment. Secondly is that the main control variable here is the distance between the source and the Geiger-Müller tube. A quick little side note here that a lot of people think that the counter is actually part of the Geiger-Müller tube, but it does actually count as its own kind of separate piece of equipment for the experiment. Thirdly is that we need to remember to measure the background count rate before and after the experiment. That's without the source in the room. And then in terms of safety, we need to minimise our exposure to ionising radiation by maximising our distance from the source at all times. And the main ways we can do that is, number one, we only fetch the source when we're ready to use it, and then as soon as we're done with the experiment, we put it away. And then the second way is that whenever we can, we stand at least 2 metres away from the source, e.g. while we're carrying out the experiment. To find the corrected count rate, you just need to take your raw count rate and subtract the average background count from it. And then once you plot a graph of your results, they should have labelled axes that include units. Mark your points with a cross rather than a dot, and make sure that your scale utilises at least half of the available graph paper. Then you need to draw a smooth line of best fit and then read off the time interval taken for the count rate to halve. Hopefully this has proved useful. Any questions or comments, get in touch below.